Open a recipe blog and search for caramelized onions. You will find hundreds of results promising deep, golden, jamming ribbons in just 10 minutes. These 10-minute timelines conflict with the actual chemistry of the vegetable. Blast an onion with high heat for 10 minutes, and the result is a basic saute. The texture softens and the edges might singe, but the chemical pathways that create deep sweetness remain largely inactive. Achieving the mahogany-colored strands required for a proper French onion soup typically follows a different schedule, closer to 45 minutes on medium-low heat. This gap between the recipe and the results exists because true caramelization is the product of 3 distinct chemical reactions, each with its own thermal requirement. By examining these reactions, the 45-minute wait stops being an inconvenience and starts becoming a predictable outcome of physics. We have to start with the composition of the onion itself. Physically, the vegetable is 89% water by weight, with the remaining 11% comprised of cellular scaffolding, sugars, and sulfur compounds. This graph shows pan temperature over time. While liquid water remains on the surface, temperature stays exactly at 100 degrees Celsius. To start browning, you must evaporate nearly all water inside the onions, a phase taking 20 minutes. During this window, the onions are sweating. They become translucent and shrink to 1/3 of their original volume, but the color remains pale because the temperature is still capped by the water content. This phase is dedicated to clearing the thermal path. Browning reactions only begin once the surface is dry enough for the temperature to climb. Once the water barrier is removed, the surface temperature finally rises above 100 degrees, activating 2 parallel browning mechanisms. The first is pure caramelization. This is the thermal decomposition of sugar, a process that occurs when heat causes sugar molecules to break apart and reform without the need for proteins. Fructose breaks down at 110 degrees Celsius, creating pale gold color at minute 25. Glucose and sucrose need 160 degrees, deepening the color to amber. These sugars lose water, recombining into aromatic compounds like furans and maltol. The shifting colors in your pan serve as a visual thermometer, indicating exactly which sugars are currently hitting their critical breakdown points. While sugars are decomposing, a second mechanism called the Maillard reaction runs in parallel. Maillard requires a reducing sugar and an amino acid. Above 140 degrees Celsius, the amino acid's nitrogen group bonds with the sugar's carbon. This triggers rearrangements, forming dense brown structures called melanoidins, providing the savory, meaty backbone of caramelized onions. Baking soda alters the environment's acidity. Raising the pH from 5.5 to 8 makes the amino acid lose a proton. This allows nitrogen groups to attack sugars faster, accelerating the Maillard reaction by up to 70%. However, this alkaline environment also rapidly breaks down the pectin in the onion cell walls. The onions often turn into a mushy puree before the slower, complex flavor pathways have finished developing. While you can use pH to increase speed, the trade-off is a loss of structural integrity and a less nuanced flavor profile. There is a third reaction that is often overlooked. The sulfur compounds that make you cry when cutting raw onions rearrange under heat into 5-membered rings called thiophene. Thiophene are responsible for the roasted, meaty depth in the final dish, but their formation depends on sustained heat applied over a long duration. Impatience often leads cooks to turn the heat to high in an attempt to speed up these timelines. High heat pushes the surface temperature toward 200 degrees Celsius before the internal water has fully evaporated. At these temperatures, the flavor compounds oxidize and degrade into bitter, burnt carbon. To prevent this, you can use a splash of water to dissolve the concentrated layer of sugars and proteins, the fond, back into the onions. This deglazing step also acts as a thermal reset, pulling the pan temperature back into the safe browning zone. A heavy cast iron skillet helps maintain this environment. It acts as a thermal flywheel, holding steady heat and preventing spot burns common in thinner pans. Using medium-low heat protects the ingredients, keeping the pan within the narrow 60-degree window between deep flavor development and total carbonization. When we combine these requirements, the 45-minute timeline becomes clear: 20 minutes for dehydration, 10 for sugar breakdown, and 15 for deep Maillard and sulfur synthesis. High heat bypasses these phases. causing onions to burn before reaching essential chemical markers. The onions aren't slow. They operate at the exact pace their molecular structure allows. If you found this dive into kitchen science helpful, subscribe for more. Tell us about your worst caramelization disaster in the comments, and let us know what you want us to investigate next. Effective cooking is less about commanding the ingredients and more about setting the optimal stage for chemistry to complete its work.